customer-driven technology, CDT, based out of Kansas City right now. I deal predominantly with Creo Simulate and mechanism dynamics, piping, cabling, and other Pro-E products with PTC. We will be talking about all the new enhancements within Creo Simulate, Creo 1.0 Simulate. Before we get started, Rosalinda has a little poll for you guys to go through. So if Rosalinda, you can go through the poll right now, and we can get started later.
Here we go. We have 2 more to go.
We done with the polls right now?
We have 1 more to go.
Okay.
Here's the last one. Okay, it's all yours, Sukumar.
Thanks much. Alright, to start off with, let's talk about all the new enhancements with the Creo Simulate. So I'm going to go over step by step. Can I give you a basic introduction to it? And we will also go ahead and do a demo session where I'm going to go through some picks and clicks, kind of showing you all the new stuff, and then we'll have a little bit of time for Q&A. So to start off with, Creo Simulate right now is an app. Okay, it can be installed or uninstalled separately from Pro Engineer. If you look at Wildfire 5, it was a part of a Pro Engineer install. It couldn't be installed separately. So now you can actually install only Creo Simulate on a machine without installing Pro-E on that. All right. Now you have an embedded mode for Creo Simulate, just like how in Wildfire 3, 4, and 5 we would go applications Mechanica. Right now we can go applications Creo Simulate. Or you can also have your standalone, more like an old independent Mechanica side. Okay, both of them have the exact same interface, right? And it's really simple to use and access. Now, the Creo Simulate has the same user interface as Creo 1.0. It has its own ribbon tabs. Icons are grouped according to their similarity with each other. For example, all the constraints together or all the loads together. We can again go ahead and customize these ribbons to where instead of you switching between tabs to pick different things, you can have a custom tab and then put icons from different predefined tabs into your custom tab, and that way you're never switching back and forth in tabs. Unit enhancements, you see that the system you want, get the stress results in millimeters, or also not valid. For example, when you do the moments are grayed out, right? Now see that the rotational constraint are valid. Improve. You have set for certain options and put it in that particular directory, so they don't have to reset. The machines with the in terms it works, it's not really disclosed, but what they told me is that they have improved the way the RAM's being used in terms of calculations. Alright, so one of the first enhancements that we're going to talk about is meshing. In meshing, you see you have a couple of new options. For example, if you look at the picture on your right hand side, it's an extremely thin part. Now if you create a regular solid model mesh, it's going to take you about 10,000 elements to probably mesh it. Now, we don't want to sit around and wait for 10,000 elements to be created, so we end up using shell elements. Shell elements are not bad, but you don't really see what's happening through the thickness side of this thing, right? So if you want to see what's happening through the thickness of it, you might want to go ahead and create solid. So again, this was one of the holdups where, in Wildfire 5, for example, you cannot, you have to wait a long time to have a lot of elements, or you would have to create shell elements. In Creo 1.0, you have these thin element meshing where it uses bricks and wedges to do thin element meshing. So it automatically detects where there is thin areas. It can transition into thicker areas by making them tetras. This will dramatically reduce the number of elements, and it improves the solver performance. So if you look at creating a large deformation analysis for a thin structure, you can actually do it much more faster in Creo 1.0 because of that. Now you also have an ability to mesh prismatic regions with bricks and wedges. Earlier it used to be like, hey, you can use tetra and wedge, or big tetra and wedge. Okay, you could not just go and say make this brick, right? So you have options right now which will help you. Say if you have a square part, it will just make a brick out of it. Okay, so this will dramatically reduce the number of elements in the model rather than having tetrahedron elements and mesh the model. And because the number of elements is less, it is directly proportional to the solving time and the amount of time it takes to solve. Now, even with respect to your results, you can export the results into product view, and you can look at your results in product view. What's good about it is that earlier the enhancement in Wildfire 5 was, even though I don't have a seat of Mechanica, I can still look at the results of Mechanica through a Pro-E seat. What if I don't even have a seat of Pro-E and I want to look at the result? That wasn't possible in Wildfire 5. Now you can do that through Creo Simulate 1.0 by just going through the simulate mode and say, results mode, and say, export the results to product view. Now, before we get started with furthermore, I want to stop right here and go ahead and do the demonstration for these two, so kind of like stays fresh. As you hear about it, you also see it real quick. So here is your Creo Simulate. If you look at the very top, you have all your ribbon user interface, all your loads, constraints, materials, all grouped together. Right here, I have different tabs right here. You can close down the ribbon if you don't like them. You can make it big. You can use your command line and say load, and it tells you where to go, where to find them. So all these are very consistent with your Creo 1.0 interface. So right now I'm going to try and create a mesh in here. So let's go say AutoGem, and let's go create a mesh. Now you can see it's going to be a little while before it creates a mesh. The reason being they're extremely, it's thin, and then we're trying to create solid elements. So I ran this before. It created about 10,000 elements for me when I did this. So just going to be a couple of seconds while I do that. Now also notice that you have different tabs, and you can actually create your own tab, and where you can get icons from, say, Inspect tab, you can get icons from Tools tab, Home tab, a Refine tab, and put them all together, so in that way you don't have to switch back and forth. Alright, so you can see right here it says it has 10,436 elements right here. So what I'm going to do is I'm going to close this, and I'm going to delete what we had, and I go to AutoGem Control, thin solid, and I can say detect thin solids. So I say detect all the thin solids with a thickness of 1.5. So right now you can see that it creates all these thin solids for me. So now if you go do an auto gem, you could see the number of elements would be around in the 400 range, and the elements are much bigger, they're thinner, and it's very few compared to what we had earlier. So you can see it's 399 elements instead of having 10,000 elements. All right? So this kind of really helps to speed up the process. Now also wanted to show you guys a couple of things. If you use, let me go ahead and get rid of that. You can see the icons here which are more. So let me go ahead, pressure load. Notice instead of picking intent surfaces and say I want to have 10, and you can preview. You have those are the couple of enhancements. We can go deformed, shell element. We could always, in order to see solid elements, which would again result would avoid it. Enhancement within this is that once I create this mesh, I can always go select a whole bunch of them from here and convert them into a shell pair, and then create a shell element and run the analysis. What this gives me, it gives me a good comparison as to, okay, I ran it as a shell element, I got this result. I ran it as a solid element, I got this result. Is there a difference? Okay, so you can do those kinds of things with it too. Now real quick, we can also go into a thermal mode in it. See, you can just switch back and forth, thermal mode or regular mode, and say I want to go ahead and add some heat load. Say I want to put a heat load right here, and then say the heat over there is say 300. Right? Then I want to also say I want to put a convection condition where I'm going to pick the outside surface and say convection coefficient is 10, bulk temperature is 30 degrees, and you can run a regular analysis. Say go here, run a steady state analysis, and we can also go ahead look at the results for thermal analysis real quick. So you can see the temperature distribution as to how the heat is distributed or being cooled down by the outside convection condition. Now this being said, we can always go back and forth between structure and thermal. So we can go back to structure and we can say I want to input a thermal load from the Mechanica thermal analysis that I've just ran, and I say okay, the local reference temperature is 30 degrees, and I can add this thermal load and run a regular static analysis. This will give me a result where what happens when a structural load as well as a thermal load is acting. So let's look at what happens only when the structural load is acting. Now we can copy that window and say what happens only when the thermal load is acting. Right? We can also do a combination where we say, okay, I want to see what happens when both of them are acting together. So this gives you what happens when there is a structural load as well as a thermal load acting at the same time. So we can do these kind of analysis all with the base Mechanica, and the reason I'm showing you these different analysis is more or less to show that the thin type of elements that we created supports these different analysis. All right, so let's see what the next one was. The next one was more or less exporting your results to Creo Simulate. Creo View. So let's look at another example for this. Say we have a connector part. I want you to look at a couple of constraints that is new. I mean, if you're with Wildfire 5, this was there in Wildfire 5. If you're in Wildfire 4, this would be new for you. So if you right click on these constraints, you can see that you've selected two surfaces, and you're basically creating a pin constraint saying that it's free to rotate and translate about the axis. You can say, hey, I only want you to rotate, I don't want you to translate. You can make any of them fixed or free, and this is new. Now, how did we work with Wildfire 4 when the pin constraint was not there? We would create a cylindrical coordinate system and use that. Okay, so give me a second. You also have another deal right here which talks about the force loads. So again, over here you can see how the rotation is blocked out. So in solids, if you want to create a motion where you want to allow the part to spin a little bit, then you might want to go ahead and say you want to create a pin constraint. You also have ball constraint, you also have planar constraint. A planar constraint just works as if the surface can translate or rotate in a plane, but it cannot move away from it. So planar, you have ball constraint, you also have pin constraint. So these are new. So let's go check out the results for this particular analysis. I want to go ahead and show you this real quick. So we have this. Now we can go File, Export to Creo View. All right. So you export it as, say, View 01, save it. If you have Creo View, you can just go ahead, open this particular results file, and you can look through whatever's there within it. So here's your Creo View results file, and you can spin, you can section it, you can look through what's happening in it. All right. So this is one of the enhancements that we just talked about. All right. Now going back, we're going to talk about connections. There is a lot of improvement within Creo Simulate in terms of bolted connections. Okay. So if I want to bolt two parts together, earlier I would have to use these in case I want to apply preloads, right? I could not create my own bolt model, or I cannot create a model that actually acts like a bolt in real life. I couldn't do that. So right now what you have is you can apply preloads on bolts modeled as solids. Okay. What you can do is you can create a little volume region, and your bolt and your preload will be applied to that particular volume region. It will also automatically detect the bolt axis for prismatic solids so that it knows which direction the preload is acting. So let's look at a couple of enhancements with respect to the preloading and the bolted connections. All right. Give me 1 second. Let me erase everything from my memory. Let's go here. Set our working directory. So let me go get rid of a whole bunch of things. All right. So notice that this part, or this assembly, is more in an exploded state. I can go back and say interface between the hole into which we work in the exploded state of the assembly for me to pick. Also notice the Mechanica model setting to say everything is under contact. So how You can, so those are your interfaces, and you can see in that gray individually contact to say bonded or free or whatever you want. All right. Now let's go ahead and run an analysis on this model. So what I'm trying to simulate here is I'm going to put these bolts in here. I'm going to tighten them up such that there's 1,000 newtons of preload. Now, how would I apply a preload? Here's the icon for it. All right. Load 1, load set 1, prismatic, volumes. Just go pick that volume region and say there is 1,000 newtons of load on it. It automatically detects the prismatic volume region's axis and determines which direction the load is acting. So here I'm going to say 1,000 again. So I'm going to do it for all the 4 bolts real quick. And I'm going to show you a couple of cool enhancements that you will really like. This will kind of give us to more accurately model a real world situation than the previous versions of the software. So there you go, we have applied those 4 bolts, 4 loads in there. Now note that I want to simulate when I tighten the bolt, it is going to compress the part, and I need to know what kind of stresses are induced in the part because of that. Now, because I put all the bolts in one load set, it's like I'm trying to tighten all the bolts at once, which is not realistic. I mean, maybe there's a robot which does that. But if I'm going to do it manually and I'm going to go into first I do this, second I do this, and third and fourth, I might want to go ahead and put them in different sets. So I'm just adding a new set for each load. That's all it is. So I just added 4 different load sets so that I can apply each load set at different times. Now I also want to go ahead and put a force load on this surface. Now here a new enhancement would be total bearing load at a point. So I say total bearing load at a point. I'm going to pick a point right here and say it's acting in the Y direction at 1,100 or 10 newtons. And you can look at the preview because it's a bearing load. So if I stick in a rod in there and then push the rod up, notice that the front half of that particular hole kind of gets pushed up and the bottom half pushed down. Some more exact simulation of what's happening in terms of what happens in the real life. So then let's say displacement, we're going to go ahead and fully fix these particular surfaces. So fully fix, I don't want them to move. So right now we're pretty set to run an analysis. If you run an analysis right now, it's going to tell you what happens if all the 4 bolts and the load are applied at the same time. But if you want to look at the result to where I want to know what happens if I go step by step, if I tighten bolt 1 and then tighten bolt 2 and then tighten bolt 3, 4 and then apply the load, what will happen? So you can set that up because you have this new enhancement within the analysis box. So if I say new static, in new static I have nonlinear load histories that I can use. Right, this box. If you uncheck it, then it's just like regular Mechanica, right, what you always had. If you check that, what it gives you is you can control when load 1 acts and when it acts, when load 2 acts, when it acts. So if you look at these functions, notice I have 4 functions. I'm going to edit function 1. All it is just a table. Say at time 0, the value of the load is 0. At time 1, the value is 1. Now the value is not 1, it is multiplied by this factor. It's more of a factor. The load, if this value right here is 0.5 and the load is 1,000, then the value of the load is 500. So notice that function 1 starts at 1 second and is applied till about 5 seconds. Okay. Similarly, function 2 is starting to apply at second number 2, at 2 seconds, and then it stays till 5. So at 1 second, function number 2 is not acting. Similarly, you have function number 3, which starts at 3rd second, 4, and then you also have 5, which is right here. So what I'm trying to say is, if I say the first bolt uses table 1, right, second bolt uses table 2, third bolt uses table 3, fourth bolt uses table 4, and the fifth bolt uses table 5. So what this does is that for the first 1 second, only the first bolt load is applied. After that's applied with its preload, it's fixed in place, then the second one's applied, then the third one, then the fourth, and then finally the main load. So if you look at an animation of this, so let's say we want to look at what happens when all the preloads are applied at once. See that? So I'm going to slow it down. See, it's like all the bolts are tightened at once, including the load which pushes this thing up. See that? All the loads are applied at one time. Now, if you want to compare that with what happens when, I think I picked that up. What happens when each bolt is tightened according to the order that we put the loads in? So see, the deformation is different. So this is bolt number 1, this is bolt number 2, bolt number 3, 4, and then you kind of push this up. So what it gives you is you can control during an analysis if the load runs from the start to the end of it, or does it start 2 seconds after the analysis and ends 2 seconds before the analysis ends. So you can control the time through which the load is acting in an analysis, which gives you a much more realistic representation of what's happening in real life, right? So a couple of enhancements here that we can look through. This is again one of the much more cooler enhancements. You earlier had no choice to pick, say, a particular area and say, I want brick elements here, or I want tetra elements here. You could not do that. Right now, you have this mapped mesh control where you can pick an area and say, I want brick elements and I want 4 rows and 3 columns. You can do that, which will give you much more accurate modeling over there compared to having whatever ProE gives you in terms of AutoGen. Now, here within nonlinear structural analysis, you can see that you can do plasticity in large deformation analysis, which is new. You can also include hyperelasticity and contact effects in the same analysis, and also use load histories. These are something that's really new within Creo Simulate. So let's look at another example real quick. So we have our stapler assembly. All right. So I want you to see right now I have a few loads. Few constraints. So I'm going to go base fixed. You can see that I've fully fixed the base of it. Okay. I'm going to pick the side of this stapler and say I can only translate in the X and Y, and I'm fixed in the Z. The Z direction is this way. You can see which way the Z is right here. So it can only go up or down, right? But it cannot go this way. Now, I'm putting a constraint at the top. This is another thing that I want to show you. you can use something called a prescribed displacement. So in here, I'm saying it can only move a maximum of -1. So it's going to go down. Okay, that top surface. So that's like a constraint which is going to actually act like a load. So within here, I'm going to go ahead and add a material property. So material assignment. Say I use aluminum. You can see this is aluminum. And then I'm going to make a copy of it. Go to the properties of it. And notice this is an isotropic linear. So I want to change it to elastoplastic. I want to edit and say import any material text data that I might have. See that? So I'm going to make it more of an elastoplastic material and this material would be used for the staple, and aluminum would be used for the base. We don't want that to be elastoplastic. Also, in terms of meshing, if you go to control, you look at map mesh, we can go ahead, pick a couple of those surfaces, and notice how you have an option to increase or decrease the elements over there. I'm going to not do it on this side so you can see the difference. We can go ahead and mesh it real quick. I want you to see right here. That's more of a map mesh because this whole stable thing is going to bend over there. So this angle is almost going to be like flat. So you want to have more clear representation because there's going to be a bunch of stress concentrations. It's much more accurate if you have brick elements. So I'm going to create brick over there. And you notice on this side, when I don't create those brick elements, I don't get much clearer localized results. Okay. So once I do this, you can also go ahead and add some contact interfaces. So I go interface. I'm going to pick contact, pick that surface and that surface, and similarly go here and pick that surface. Is going to contact with that. All right. So once we do this, we have to go ahead and set up our analysis. In our analysis, I want you to see I have two constraint sets right here. You have constraint 1, which is for the fixed, where everything's fixed. You notice that it starts at 0 and it ends at 1, and the value, it's constant, it's always applied regardless. Now let's look at up down. And I want you to see here that I have 0, 0.5 and 1 as the intervals. At 0 the value is 0, at 0.5 the value is 5.8, and at 1 second the value is 0 again. So what happens here is that this up down is actually applied to the tabletop constraint. So if you do an edit definition on this one, you can actually see at time is equal to 0, this value is 0 times -1. At time is equal to 0.5, this value is -1 times 5.8. So this is going to be forced to move down to 5.8. And then at time is equal to 1, the value is 0. So this is going to go back to its original position. So this is how you would use a prescribed displacement analysis that you can perform on this table. So let's look at the result for this. So let's say I want to look at what happens at time 1 second, and I want to animate it and I want to deform it. So we can see as to when the time hits 0.5 seconds, it's going to move up to 4.58, 5.8, and then it's going to go back up. So notice it's an elastoplastic material. You can see how the stress kind of changes in the part throughout the whole analysis. All right. So that's another enhancement that's pretty cool. Now, if we do a lot of welding, we have an enhancement over there where we get to kind of animate the welding process. What's new in here, or how this works, is that you can actually apply a heat load on a composite curve. Okay, so you can apply a heat load on a curve, and heat loads can change as a function of arc length. These are the two enhancements that will help you simulate a weld process. So when you're moving from, say, this location in that way, you can see how as you pass, you see the temperature distribution in the rest of your geometry. Okay, so that is another enhancement that we will be talking about. We're almost done. We have this, and then we'll do a little Q&A, and we should be good to go. So let me go ahead and set my working directory. Working directories are very important. So right here we are in the thermal mode. So you have all these boundary conditions set. So let's apply a heat load. Heat load on a curve. Now I can right click and pick from the list. Notice it highlights the whole curve in green right there. We can go ahead and pick them. Now you can say I want to apply load per unit length, and it's going to be a function of arc length, and the time variation is going to be a function of time. You can choose to combine, notice this, combine the spatial variation with the variation with respect to time. So you can combine them, which is also another enhancement within it. So you can look at the function. You're trying to tell here that as your heat load moves at a certain pace, how does the intensity change? So if you do a review, say at time equal to, say I want to do it for 400, and say the upper limit is 1000 in terms of S, you can see the graph. So as to how the temperature peaks at that time. That's the heat load that acts at any particular point of time. You can keep changing the time, and this whole thing can move. Okay, so, and then say the value of the heat load is 30,000, and we can run an analysis based out of that, and you can look at the result that you get as to how your heat load travels with time and how the temperature is being distributed throughout the part. So you can see how that's your weld that travels, and you can see how the temperature distributed throughout the time. Right? Again, this is possible only because we can add a heat load on an arc, and we can change the heat load as a function of arc length. These are the two enhancements that enable us to do this. All right. So I can go more. There's much more to go, but it's almost 12:50 Central, so I want to stop and have a little time for question and answers. So Rosalinda, can you unmute the audience?
I actually have some questions in the queue. They've typed some questions
Okay.
in. Mike has a question. I'm not sure if you covered this or not. You may have. Is contact analysis possible with shell elements?
No, sir.
Okay, Donald has two questions. The first one is, do you still have to run the preloaded analysis once and then adjust the value of preload and run the analysis again?
No, sir, you don't have to do this. This will kind of help you avoid running two analysis, which is the pre-stress analysis, right? You don't have to do that.
And then he goes on to say, per help document in Wildfire 4, understanding preload and tensile force in advanced fasteners. I'm not sure if he can clarify that.
Yeah, can you unmute him so that he can talk?
Sure, if he's able to. Okay, Donald, do you have a microphone at all? I've just unmuted you. Oh, he just said you answered the question.
Okay. Okay. Anything else? I mean, like, can you just can I just unmute everybody so that they can talk?
Not a problem.
Okay.
Muted.
I hit unmute all, but it's not. Okay. I'll just unmute everyone, just so that some people might have questions on the fly, too long to type or whatever. Guys, you can please shoot your questions. There are much more enhancements available to Creo Simulate than what I covered. I only covered like about 10 of them. There are like at least 40. The time constraint is one. There's a lot of enhancement in terms of dynamic analysis too. And we can actually do radiation, gray body radiation. I didn't even cover that, which is, lack of time. So any questions on whatever we covered, I'll be happy to answer, and I'll just put up my contact information real quick. Why can't I show my sticky note? Right. That's my email. I hope it's big enough for people to see. I don't know if I can change the font of it, but please feel free to email or call with any questions that you have about this or anything that you might have with respect to the whatever you guys have.
Feel free to shoot me any questions as well. Suk, there is one more question. Oh, you see it?
Yes, I'm
sorry.
Yeah, I'm actually. When constraints lose references, do you have to start? Can you elaborate? There's a question which says, when constraints lose references, do you have to delete and restart? Yes, when you actually say, for example, you apply a constraint, to say, for example, a hole, and then you delete the hole. When you delete the hole, you're actually given a notice that if you delete this, its Mechanica dependents will also be deleted. So you don't have to delete and restart. It will delete itself when it loses the reference.
If there are no other questions, you want to close things down, Suk?
Yes. Yes. Alright, guys. So this is my contact information. You can always call or email. Feel free to do so. Alright. Thank you so much for being here with us. Appreciate everybody's presence. Thanks a lot. Alright, Rosalinda.
Yep. Everybody have a great day.
Thanks.